In this experiment, students would investigate the variation of the degree of superheat with the refrigeration load of a reciprocating refrigeration machine operating at constant condensing pressure and under the control of a thermostatic expansion valve. The equipment to be used for carrying out this experiment is the refrigeration laboratory unit manufactured by P.A. Hilton. It consists of a twin-cylinder compressor driven by an AC motor through belt and pulleys, a water-cooled refrigerant condenser, a thermostatic expansion valve and evaporator. Input heat load to the evaporator is generated artificially by electric heating elements at the evaporator under the control of a variable transformer. The refrigeration unit is equipped with the necessary instruments and devices for measuring flow rate, pressure, and temperature of refrigerant and cooling water at various locations, and a dynamometer for measurement of motor torque output, and a handheld tachometer to measure rotational speed of the compressor. The motion of cylinder compressor is powered by an AC motor through belt and pulleys. The refrigerant would be compressed and pushed to the condenser. When the refrigerant flows through the condenser, some of the heat energy would be absorbed and carried away by the cooling water. Then the refrigerant passes through the liquid-to-vapor heat exchanger. At this process, higher heat energy of refrigerant flowing from condenser would be absorbed by the lower heat energy of refrigerant from the evaporator. When the refrigerant passes through the expansion valve, its pressure would be lowered. At this moment, the temperature of refrigerant is very low. An electrical heater is equipped at the evaporator. Students can adjust the loading along the experiment. At this stage, refrigerant with low heat energy would absorb and carry away the heat energy generated from the heater. The refrigerant coming out from the evaporator may have lower heat energy than that coming from the condenser. So heat energy would be transferred in the heat exchanger again. And then the refrigerant flows back to the compressor. This is the refrigeration cycle in this equipment. In stage 1, students should familiarize with the setup of the equipment first. Before switching on the power, please ensure that the cooling water supply for the condenser is turned on and maintained at the maximum flow rate. Also, please check if the electricity is properly connected. Adjust the flow rate of cooling water through the condenser at about 40 grams per second. Set the evaporator heat input control to the minimum position by turning the control knob fully anticlockwise. Ensure that the diverter valve is set such that liquid refrigerant is diverted to pass through the liquid-to-vapor heat exchanger. Now, switch on the unit, and let the unit run for 4 to 5 minutes to allow it to achieve steady operation. Increase the heat load to the evaporator in steps of about 200 watt, and adjust flow rate of cooling water such that the compressor discharge pressure is maintained within the range of 900 kN per square meter. Remember, allow the unit to achieve steady operation after each step of load increment before taking your readings. To adjust the evaporator heat input rate, please calculate the product of the voltmeter and ammeter readings. It is the formula of P equals V time I. To read the gauge pressure, the unit is in kilonewton per square meter. As shown in this photo, the gauge reading is 800 kilonewton per square meter, which equals to 8 bar. The absolute pressure is the sum of gauge pressure and atmospheric pressure. Read the example here. Shaft power output of the motor is to be measured by using the spring balance, which gives reading of the free acting at the arm for balancing the torque developed. To obtain the reading, move the upper end of the spring balance until the spring balance reading. Rotational speed of the compressor shall be measured for each test run by using the handheld tachometer. The mass flow rate of refrigerant is measured by the R13 for a flow meter, and the values of specific enthalpy are read from the pH diagram. We assume there is no pressure loss in the system. The suction pressure P1 is equal to evaporator pressure, and the discharge pressure P2 is equal to condenser pressure. The temperature values of refrigerant in different refrigeration process can be read in the screen, from channel 1 to 6. As mentioned, repeat the procedures with increasing heat load to the evaporator in steps of 200 watt until the load reaching 1000 watt. And remember to allow the unit to achieve steady operation after each step of load increment before taking your readings. After the test, turn the evaporator heat input to 0, and after 1 minute, switch off the electricity supply, and then turn off the cooling water. Remember to record the data in table along the experiment. Then draw the refrigeration cycles on pH diagram, and you could obtain values of specific enthalpy on the diagram. First, draw the pressure lines. Pay attention to the unit of pressure used on the diagram. Point the compressor suction temperature of refrigerant T1 on the right-hand side of evaporation pressure line. Then point the compressor delivery temperature T2 on the right-hand side of condenser pressure line. Line up 2 points, and you get the compression line. Point the expansion valve inlet temperature of refrigerant T4 on the left-hand side of condenser pressure line. Draw a straight line vertical down to the evaporation pressure line. You get the line of expansion. Now, the refrigeration cycle is drew. Draw the cycles of other sets of data on the same diagram like this. Let's come back to our experiment topic, refrigeration system superheat. In ideal case, the refrigerant leaves the evaporator and enters the compressor as saturated vapor, and the refrigerant leaves the condenser as saturated liquid, the compressor exit pressure. Hence, the ideal refrigeration cycle looks like the green lines. So, why differences are made at the leave of condenser and at the leave of evaporator? It is because a liquid-to-vapor heat exchanger is equipped to subcool the liquid refrigerant leaving the condenser by using colder, low-pressure vapor from the evaporator. At the same moment, the temperature of low-pressure vapor coming out from the evaporator is raised, superheat. Superheat and subcooling improve efficiency by increasing the refrigerant subcooling, boosting cooling capacity, and helping prevent liquid refrigerant from entering the compressor. How do superheat and subcooling raise the coefficient of performance in refrigeration? When we calculate the coefficient of performance of the refrigeration, it involves the rate of heat removal from refrigerated space, and the power input to the compressor. The two items vary with values of specific enthalpy. The subcooling and superheat would increase the difference of H5 to H1, that is the rate of heat removal from refrigerated space QL increase. So higher QL results as higher COP. You may get the concept now. In the logbook report, please complete the refrigeration cycles and calculations. Then try to do the supplementary. Enjoy the experiment. Thank you.